Hello students, welcome to the fourth lecture of linear algebra. The topic for this and the next few lectures is going to be positive definite matrices. Okay, these matrices play a wide variety of roles and arise in a wide variety of contexts. We will try to lay the foundation by giving the definitions and investigating some basic properties. You might have come across these matrices already in a previous segment. Okay. So let's start with the definition without any delays. First of all, positive definiteness is a property defined for square matrices. Right? So we don't really talk about a fat or a thin matrix being positive definite. Okay? Further, the definition of positive definite matrices or positive definiteness ties in closely with the notion of a quadratic form. Okay, it's for that reason we will also assume that the matrix is square symmetric. Okay, so we'll assume that the matrix is square symmetric. Okay, this will become clear in a minute. So given a matrix A, we say that it is positive definite. Just use the shorthand PD for now. It's positive definite if is the definition x transpose AX. This is the quadratic form corresponding to A. Correct? So quadratic form is positive no matter what x is. Okay, for any x, that's the key here. For any x, quadratic form is positive. Now one thing I have to immediately say is that obviously if you set x to 0, then the quadratic form becomes 0, right? There is no point to that, so we just say x not equal to 0. Okay, so long as you pick a non-zero x, the quadratic form is always positive. Okay, that's the definition of a positive definite matrix, right? This can also be restated as the Rayleigh quotient being always positive. Okay, the Rayleigh quotient is always positive. That's the definition. Another way you can define the same thing. Okay, now why do we assume square symmetric? Because as we said before, whenever you are dealing with quadratic forms, we can always assume without loss of generality that the underlying matrix A is square. Okay, because if it is not square, then I can simply rewrite this as x transpose A plus A transpose by 2 times 6. If it's not symmetric, I mean, if it's not symmetric, they can rewrite it as x transpose A plus A transpose by 2x, and this matrix inside happens to be symmetric. Okay, so there's no loss of generality in assuming whatever is inside here is symmetric. So we're going to assume square symmetry. Okay, many books and texts will actually write it as symmetric positive definite. Okay, but for our course, we'll assume that the symmetric word is there by default. Okay, so whenever we say positive definite, we are only referring to square symmetric matrices. Okay, so this is the main idea, right? All quadratic forms, any quadratic form, no matter what variables you pick, is always positive. Right? Now, why is such a setup even interesting? We'll recall that one of the main motivations for us to define quadratic forms was cost functions. Right? And when you talk about the cost of something, for example, we looked at this in the last class, right? So we had x1 minus x2 whole square plus x2 minus x3 whole square. So we had a signal x1, x2, so on up to xn, and we are looking at the cost function as how much the signal varies from one coordinate to the other. And this is how we set up the cost function xn minus 1 whole square. Now as you can see here that this cost function is the sum of squares, right? It's the sum of non-negative numbers. So you can see that this cost function is always going to be greater than or equal to 0. Okay, there is no context under which it's actually negative. Okay, so we do often encounter cost functions that are never negative, right? So it makes sense in that context to define a positive definite matrix. Okay, fine. Now, one important thing to note for positive definite matrices, and we'll see this analogy play along, throughout this lecture, is positive definite matrices play the same role as positive numbers. Okay, I'll explain this in a minute. So for example, if you think of matrices as being analogous to real numbers, okay, suppose if you build an analogy, think of matrices as being lifting up of real numbers. Real numbers are just 1 cross 1. You generalize them, you get matrices, right? So whatever relationship positive numbers have to real numbers, you can think of positive definite matrices having a similar sort of relationship to matrices. Okay? In some sense, a positive definite matrix is like a positive number. A lot of properties that you will see will actually be very similar to the properties of positive numbers. For example, we're going to say later in the lecture that a positive definite matrix has a square root. Okay, we know that positive real numbers have a square root. Negative real numbers do not have a square root. If you stick to real numbers, in a similar way, negative definite matrices or what we call indefinite matrices do not really have a square root, whereas positive definite matrices do. Okay, we'll look at many such properties that keep playing around. Okay, so so with that, let me actually also define negative definite matrix. We don't actually use it. A is negative definite if x transpose Ax is less than 0, no matter what x is, right? For any x, of course, other than 0, right? Negative definite if x transpose Ax is less than 0 for any x not 0. Okay. Now the other way to say this is A is negative definite if minus A is positive definite. Okay, if minus A is positive definite. Sorry. Okay, correct? Because if you actually put minus A in place of A, here you get minus x transpose Ax, and this inequality actually means that x transpose minus Ax is always positive. So minus A has to be positive. Okay. Given a matrix, it doesn't have to be either positive definite or negative definite. It could be what is called indefinite. Okay, it's indefinite if x transpose Ax greater than 0 for some x and x transpose Ax less than 0 for some x. Okay, so I'm actually able to find an x, a set of variables, such that the quadratic form is positive. I'm also able to find an x such that the quadratic form is negative. Okay, that's an indefinite matrix. You could also have indefinite. Let's take an example, right? Since we're dealing with quadratic forms, so let us consider, for example, this quadratic form in two variables, x1 square plus x2 square. Okay, this quadratic form corresponds to the identity matrix. So if you have to actually write this as x transpose Ax, the A will be equal to the identity matrix. Correct? Now this x1 square plus x2 square, is by looking at it, you can easily see is always positive, isn't it? The only way to make x1 square plus x2 square 0 is actually make both x1 and x2 to 0. That means you make the vector x to 0. Correct? So since we are excluding that, so this is actually positive. So this matrix is positive definite. Okay. Similarly, if you take the quadratic form minus x1 square minus x2 square, this is negative definite. Okay, for the same reason. Correct? The corresponding matrix minus 1 0 0 minus 1 will call as negative. Correct? Now what about this quadratic form x1 square minus x2 square? Okay, the corresponding matrix is 1 0 0 minus 1. Okay, now this matrix x1 square minus x2 square is indefinite, because if you set x1 equal to 0 and x2 equal to 1, you get a negative number. If you set x1 equal to 1 and x2 equal to 0, you get a positive number. Okay, so you get both negative and positive. Okay, it doesn't stay always negative or always positive, so it's indefinite. Okay, fine. So this is the definition of positive definite matrices. Okay, now going along with this analogy that I just mentioned, right? Building on this analogy, we use a very powerful notation. We say if A is positive definite, we simply write A bigger than 0. Okay, we write A bigger than 0 to mimic the similar inequality that you would write for positive real numbers. If x is if let's say A is a positive real number, you'll write A bigger than 0 to mean it is positive. Correct? So we use the same notation for matrices, even though we understand that for matrices it means something completely different. It actually means that the corresponding quadratic form is positive no matter which set of variables you pick. Okay. So this is the definition of positive definite matrix. Now let's look at one defining theorem or a defining property of positive definite matrices. Okay, the following, right? A bigger than 0. So A bigger than 0 once again means A is PD. A is PD. That's what it means. A is bigger than 0 if and only if. Okay, so note that this is an if and only if statement. All eigenvalues of A are positive. Okay, all eigenvalues of A are positive. So this is an equivalent characterization, okay, in the sense that also this is much better than the definition, right? Because let us say that I hand you a matrix A and I ask you to check if it is positive definite or not, right? If you go by this definition, what should you do, right? I should try to pick every possible vector x that there is, compute the quadratic form and check if it is positive. That's what I should do, right? I should go through every possible x. And of course, the number of such x uncountably infinite, you can't really go through all of them, right? So this definition is not, in some sense, you cannot directly use it to check if a matrix is positive definite. But this theorem you can, right? All this says is, to check that a matrix is positive definite, all I need to do is find their eigenvalues and make sure that the eigenvalues are all positive. Okay, there are algorithms to find the eigenvalues to a reasonable level of accuracy for any matrix. We discussed one of a crude version of such an algorithm earlier. Right, so you find the eigenvalues and then check their positive. So this is much more workable, this definition, okay, or this theorem than the definition. Okay, fine. So how do we prove this, right? The proof of this is quite straightforward, but just to be very clear, let me run through the proof in a lot of detail, because this is an if and only if statement, right? So whenever you have an if and only if statement, you need to prove it both ways, as we saw in the beginning of the course as well, and you had some exam problems also that asked you to do if and only if. Okay. To prove if and only if, I need to prove two things, right? First, I need to prove that if A is positive definite, then eigenvalues appear positive. This first part I have to prove, right? The second part I have to prove is if eigenvalue is positive, then A positive definite. Okay. This is actually quite a simple theorem. We won't really need to do so much, but I'm just going through it just so that we have it, we go through it properly. Okay, we have to prove both things, right? The second statement here, as you see, is like the reverse of the first statement, right? The reverse. We have to prove that if this happens, then this happens, and conversely, if this happens, then this happens. Okay? That's what you need to prove. Okay, so let's prove the first part, right? To prove the first part, you're already given that A is positive definite, correct? What does that mean? No matter what x I pick, x transpose Ax is positive, right? So in particular, I can pick x to be an eigenvector of A, right? Then what is x transpose Ax? If x is an eigenvector, then x transpose Ax is equal to lambda, the corresponding eigenvalue. But A is positive definite, that means that this quadratic form is positive, that means eigenvalue is positive. It doesn't matter what eigenvector I pick, the corresponding eigenvalue turns out to be positive, meaning all the eigenvalues are positive. Okay, that finishes the first part. Now to prove the second part, if the eigenvalues are positive, then A is positive. Here is where you use the Rayleigh quotient theorem, right? So remember, lambda min x transpose x is less than or equal to x transpose Ax is less than or equal to lambda max x transpose x, right? Now what does it say? If all the eigenvalues are positive, that information is given to you, then you know that lambda min is positive, correct? If lambda min is positive, then this whole thing here on the left side is positive, right? Remember, x transpose x is positive, x is some non-zero vector, x transpose x is positive, right? So this whole thing is positive, right? And what you have here is x transpose x greater than or equal to a positive number. Maybe this positive number is like 0.1 or 0.001, some illustrative example, which means x transpose Ax is definitely positive. Okay, so which implies that x transpose Ax is positive, or in other words, A is positive definite. Okay, right. So this property is the central property. In some sense, everything else that you see in this lecture, right, any property that you see can be proved either from the definition, which is this one, either from the definition or from the eigenvalues. Okay, so if you remember these two things, you will be able to do everything else very smoothly and very quickly. Okay, very good. So let us now talk about some very important properties, okay, of positive definite matrices. Okay, why do we talk about properties? Because it helps us in understanding, right? So if you're given a matrix, can you very quickly check if it is positive definite or not, right? Of course, you can find all its eigenvalues and check, but what are some important properties that will help you decide very quickly? Okay, and we'll also try to look at some applications where positive definite matrices do come up. Positive definite matrices will come up when we do least squares, they'll come up when you talk about any covariance matrix and probability. That includes covariance matrices, also includes PCA. They'll come up when you do PCA. Okay, and many other scenarios. So in some sense, as I said, they are as elementary to the set of matrices as positive numbers are to the set of all real numbers. Okay, so let's look at, without any further delay, let's look at properties, right? So if, let's say, a matrix A is positive, definite, then let me write down something. Some of these will actually be very immediate and obvious to you. Trace of A is positive. Somebody tell me why that is. The trace of A is positive. I keep forgetting that this is a recorded lecture. The trace of A is positive, right? Why is the trace of A positive? Because the trace of a matrix is the sum of the eigenvalues of the matrix, right? If A is positive definite, then we know that the eigenvalues are all positive. So the trace is definitely positive, right? The determinant of a matrix is positive. Okay. If A is positive definite, then certainly the determinant is positive. Okay. Certainly the trace is positive. Then what else? The diagonal entries of A are positive. Okay. So if you have a positive definite matrix, all its diagonal entries have to be positive, right? They cannot be negative. So if you see a matrix with a negative diagonal entry, immediately you rule it out, say it cannot be positive. Okay. Why is this true, by the way? Why is this true? Because remember in the last lecture we discussed, right, that all eigenvalues are between lambda min and lambda max for any matrix, not necessarily positive definite. Any symmetric matrix, the eigenvalues, the diagonal entries will be between the smallest eigenvalue and the largest eigenvalue. If A is positive definite, then the smallest eigenvalue is positive, so all diagonal entries are positive. Okay. Now let's try to push this a bit and actually write down something that may be slightly more sophisticated here, right? All principal submatrices. I'll define what principal submatrices are, right? Of A are positive definite. Okay. What we're saying here is that A is positive definite, then any submatrix of the so-called principal submatrix we'll talk about in a minute is also positive. Okay. Now what is the principal submatrix? We come across this concept earlier when we did the interlacing theorem as well. So basically when you have a matrix, right, and suppose I remove certain rows of the matrix. Okay, so let's say this is a 4 cross 4 matrix like this, or let's say it's a 3 cross 3 matrix. Okay, so it's got 9 entries, 3 rows and 3 columns. Suppose I choose to remove this particular row of the matrix, right? So I remove the third row of the matrix, right? And I remove, suppose, the same column, meaning that if I remove the third row, I'll remove the third column. Okay, then I am left with a matrix inside, that is this 2 cross 2 matrix. I'm left with that particular 2 cross 2 matrix. Okay, this will be a principal submatrix. Okay, so a principal submatrix is obtained by removing some rows and removing the same columns. Okay, so if you choose to remove row 3, we remove column 3. Okay, we could remove multiple rows as well. Suppose if I remove row 1 and row 3, I remove column 1 and column 3. Okay, then the resulting matrix that's left after removing these rows and columns is a principal submatrix. Okay, it's important that you remove the same rows and the same columns to preserve symmetry. Okay, if you end up removing, let's say, the third row, but you remove, let's say, the first column, the matrix that's left over will not be symmetric. Okay, to retain symmetry, you have to remove the same index rows and the same index columns. Okay, so these are what we'll call principal submatrices, right? Now what we are saying is that if A is positive definite, then every principal submatrix is also positive definite. Okay, so that's a very important property of positive definite matrices, right? So why is that the case, right? For example, here let's look at this specific example that we talked about, right? You have this 3 cross 3 matrix, right? I removed the third row and the third column, I got a 2 cross 2 matrix. How do I know that the 2 cross 2 matrix is positive definite? Well, it's actually quite straightforward to see, right? So suppose this matrix, 3 cross 3 matrix is A, then you have basically x1, x2, x3 times the matrix A times x1, x2, x3 written as a column is positive, right? For any x1, x2, x3. Okay, it doesn't matter what they are as long as they're all non-zero. For any x1, x2, x3, this is the definition of A being positive definite. Okay, just rewritten the definition here. Okay. Now, remember, I need to show this only for the top. I need to show that this top 2 cross 2 submatrix is also positive definite. How will I do that? Well, I'll just set x3 to 0. Okay, I can do that because remember, this inequality holds no matter what x1, x2, x3 are. So whatever values I pick for them, right, the inequality must hold. This must be bigger than 0, right? In particular, if I just set x3 to 0, then whatever inequality I get in terms of x1 and x2 must also be true. Okay, so if I set x3 to 0, then what do I get? I get x1, x2, 0 times the 3 cross 3 matrix A times x1, x2, 0 bigger than 0. Okay, that's what you will get. Correct. So what is this? What is this going to be? Now, if you expand this whole thing, right? So if you have this matrix A written the usual way as A11, A12, A13, A21, A22, A23, A31, A32, A33, and if you multiply it with x1, x2, 0 on the left side and x1, x2, 0 in the column on the right side, just do the algebra. What you will see that you will end up with A11, A12, A21, A22, x1, x2, x1, x2 bigger than 0. Okay, so what you get here is essentially a quadratic form in the principal submatrix. Correct? This is the principal 2 cross 2 submatrix obtained by removing the third row and third column from A. Right? And what you get is the quadratic form corresponding to this principal submatrix is positive. Okay, so you see that it sort of follows very trivially from the definition. Okay, so given positive definite matrix, any submatrix that you get by removing some rows and the same indexed columns is also going to be positive definite. Okay, very good. So in fact, I would go so on to argue that 3 is a special case of 4. Okay, in some sense 4 implies 3. If you know 4, from 4 you can actually argue 3. Okay, from 3 1 follows from 3. Okay, from 4 3 follows and from 3 1 follows. I'll leave it to you guys to think about any doubts you ask me later. Okay, fine. So that is the okay. By the way, the converse of this is also true in some sense. There is I'll just write down the theorem. We'll do a proof of this later. Slightly involved, but not beyond our reach. We'll definitely do it maybe a couple of lectures down the line. If all principal submatrices of A are positive definite, then A is positive definite. Okay, so this is like a converse or the reverse direction of what we said here in this statement over here, right? We said that if A is positive definite, then all principal submatrices are positive definite. Here saying the reverse. Okay, if all principal matrices are positive definite, then A is positive. Okay, in fact, you don't even need to check all principal submatrices. You only need to check what are called the leading principal submatrices. Okay, what are leading principal submatrices? Well, leading principal submatrices are submatrices of this type. Okay, so you pick the top 1 cross 1, then you pick the top 2 cross 2, then you pick the top 3 cross 3. Okay, and then you pick the top 4 cross 4. Okay, so this is an example for n equal to 4. Okay, this matrix is a 4 cross 4 matrix. It has 4 leading principal submatrices, right? And this is the first leading principal submatrix. Okay, this is the first leading principal submatrix, right? And then this whole thing over here is the second leading principal submatrix of size 2 cross 2. Then this whole thing here gives you the third, the 3 cross 3 principal submatrix. Okay, and then you have the 4 cross 4 leading principal submatrix, which is just the full matrix itself. Okay, So long as all of the leading principal submatrices are positive definite, then A is positive definite. Okay, you don't have to check the last one. For example, to check if this 4 cross 4 matrix is positive definite, all I need to do is make sure that this 1 cross 1 matrix is positive definite. Okay, by the way, what does it mean to say a 1 cross 1 matrix is positive definite? When is a 1 cross 1 matrix positive definite? Well, for a 1 cross 1 matrix to be positive definite, the matrix itself has to be filled up with a positive number. Okay, it has to be a positive number. As I said, positive definite matrices are a lot like positive numbers, right? A 1 cross 1 positive definite matrix is actually a positive number. Okay, fine. So to check this 4 cross 4 matrix is positive definite, all I need to do is check that this matrix is positive definite. Okay, that means this number is positive. Then check that this matrix is positive definite. Then check that this matrix is positive definite, and then you are done. Then the full matrix is going to be positive definite. Okay. In fact, to take things even further, make them even more complicated, I don't even have to check that they're positive definite. I just need to check that their determinant is positive. Okay. Have positive determinant. If it is positive definite, then definitely the determinant is positive, right? That's a weird sentence, but yeah. So all I need to do is check that all these matrices, this matrix over here, this matrix over here, and this matrix over here have positive determinants. Then A has a positive, and then A is definitely positive definite. This is called the Sylvester's criterion. Okay, we'll do a proof of this later. Okay, so we'll defer the proof. Okay, we'll defer the proof till later. Okay. In the next part of this lecture, we'll look at some more problems.